Okay, but I think we can start. So I'm going to share my screen. Okay, so what we are going to do now, as I told you before, is to create this reinforced concrete shear wall. Okay, before we have seen for reinforced concrete structures how to do beam models. Now in this case we are going to do something a little bit more complicated. So we're going to create a shear wall, reinforced concrete shear wall. So you will learn how to use shells, how to combine shells with beam fiber cross sections like this. Here we have a web wall and two boundary elements, which are beams, columns. And then I will show you how to create this kind, to simulate this kind of setup. Now this one is going to simulate an experimental test that was presented in this thesis. And of course, I will share with you also this paper, but they can be found on the website. So it is a simple shear wall, a squat wall, where basically cyclic loading is applied onto the top beam. The top beam is rigid, but is allowed to rotate, okay? Okay, so you will learn in this case how to obtain this kind of, how to do this kind of cyclic pushover analysis, how to use the shells, how to create a composite shell cross-section consisting of the nonlinear concrete model that I talked about before, and how to create rebars. Rebars are not going to be created physically, so they are not going to be lines inside this shell. We are going to do it in a smeared fashion. So we are going to define a steel uniaxial model. And then in OpenSees, you have something called plate rebar. That basically is a kind of material wrapper that's a uniaxial material for steel. The user gives an orientation angle, and it will convert it to an equivalent plane stress material, acting only on that direction. As it is a plane stress material, it's easy then to use it inside.
Yeah, I hear you. Desculpa, podes falar inglês? Não sei.
Mute. Okay, sorry. Perfect, here we are. Okay, so we're going to start from the beginning. So let me clean the output and also the input. So we start from a new file. I will try to be slightly faster on the modeling part. In the previous example, you have seen how to model line elements. So in this case, since I usually don't remember the measures of the specimen, I already have a CAD drawing of the boundary lines. So if it may happen that you have these kind of drawings and you want to import them, there are a number of CAD file formats that you can import. If you want to import an existing geometry in one of the open CAD formats such as IGS, STEP, or BREP that can be exported, for example, from AutoCAD or Rhinoceros, you can import them. In this case, I'm going to import a BREP, and you can find this CAD file inside the folder RC Wall, and it is called base drawing. Okay. So once you import it, it's just a series of lines, just lines like this, on the XZ plane. So we're going to analyze this shell structure on the XZ plane. Remember, this one is actually a 2D analysis, but since I want to show you how to use shell in 3 dimensions and how to connect shells with beams, I'm going to do a 3-dimensional analysis, even though for this kind of analysis, a 2D analysis is sufficient. Okay, so since this model is quite large, I'm going to increase the grid size. It's not important, but okay. Let's say you have a number of lines because you draw them in AutoCAD or in any other CAD, and then you want to convert them in surfaces, because now we are going to create surfaces. So here you are going to see the inner quad, which is the one of the actual shear wall. Then you have a bottom beam, a top beam, and then this surface here, which is only used to simulate the fact that this beam was made rigid, okay? Still allowed to rotate, but rigid. Okay, so when you have a framework of lines like this, there is a nice command to create planar surfaces out of those boundary lines. This command is called planar, or planar surface from planar curves. So you select planar, and then it's okay, select the inner walls or any other lines. So you select all the lines, right click, and it basically creates a series of faces, which in CAD is called shells, which is just a coincidence that in CAD we have the word shell. It has nothing to do with the shell element in finite element analysis. In CAD, a shell is a multi-surface, so many faces connected together, pretty much like a polyline for curves. Okay, so when you create these kind of surfaces from planar curves, STKO keeps the previous selection, and you can safely press cancel to remove it. Okay, so this is all the CAD that we need. Okay, a series of faces connected into a single geometry called shell. In fact, if you go here, you will see that you have many faces that build up this assembly. Okay, so perfect. Once you have the geometry, as we have seen before, we can start directly with the physical properties. Then we will come back here in the geometry to create local axes for orienting the beams, but we will do it later on. So the first thing, we go into physical properties, and we move here so we see the assignment. I don't want to see the grid, so I can get rid of it. Okay. So now everything is transparent, meaning that nothing has been assigned. So let's start with the constitutive modeling. The first thing that we need to do is to create the material model for concrete. So I already give you the explanation for the three-dimensional constitutive model. So now we are going to create this one for this example. Here already have all the material properties, but you can find them here in this paper. Of course, as any numerical test, majority of the numerical tests, you just have the Young modulus, the peak strength in compression and in tension, but then you don't have all the other parameters such as fracture energy and so on. So in this example, I had to play with them, with those values. If you have more accurate experimental data, it's better. So you can calibrate easier the constitutive model. So as I said, now we go to create a material. This time is not a uniaxial material, it is a n-dimensional material. And you can go under plugin, as the software, damage TC3D. Okay, so as I told you before, and you can see it also from the description here, first one is the Young modulus, and in this example it was 23,000. Poisson ratio 0.2. Then we have a tensile strength of 3.2 megapascals. Then a fracture energy in tension, and this one is the real fracture energy, will be automatically regularized, as I told you before, of 0.075. Once again, this number is not taken from the experimental test because there aren't here, so I had to play with it. If you want, you can play and try to obtain better results. For compression, the only data that we had, it was at 30 megapascals as a peak strength. So typically here, I choose 2/3 peak strength, so 20 is fine. Then a residual strength, in this example, I've chosen 10. Then the peak deformation, 0.003. And the compressive fracture energy is quite high, in this case, 100. Then, as I told you, these are the shape factors for the compressive curve. You can play with it, but the default values are fine. Then the miscellaneous parameters that define the yield surfaces and other stuff. For the tensile surface, I told you that we have two options, Rankine or Lubliner. The Lubliner is the one that I've shown in this paper. And it is the one that we're going to use. Where is it? Failure criteria. which is this one, both for compression and tension. So what you obtain is an overlapping of two surfaces like that. Okay, so the increase factor in biaxial compression, we use the default 1.16. This parameter, as I told you, is a parameter that goes from 0 to 1. 0 gives the maximum dilatancy this model can have, 1 the minimum. In this example, I've seen that a value of 0 was fine, but it's not that important because we don't have too much. In this example, they didn't use any vertical load, just the self-weight of the structure. So in any case, it is not so important. This factor, as I told you, is only important when you're going to do three-dimensional analysis. So here we keep the default. And for the amount of plasticity, I've used 0 for tension and 0.5. Once again, you can play with those values to obtain different curves. Integration scheme, as I told you, I always use the implex, taking care of using small time steps. And then the auto-regularization, because I don't want to get crazy about the dimension size. I just put the real fracture energy and OpenSees will take care of regularizing everything. Okay, let's say that we want to do a material test for this. So let's test it in monotonic. Now keep in mind that these fracture energy here are quite large because they are in terms of displacement jump, but they will be regularized then. And in the material tester, of course, you don't have the size of the element because it is not assigned to any element. So when you test it, it is the real one. So let's push it to a deformation of 0.01 in tension, 0.01 without the minus. Okay. Okay, this is how it looks like in tension. Of course, this one will be divided by the mesh size. So taking care that we are going to use a mesh size of about, I think, 150 more or less. So this one will be much lower. And the same in compression. Let's see how it behaves. Okay, now in this case here, you have a lot of fracture energy, but also this one will be divided. And if you want to have a look at how it behaves cyclically, let's push it here to 0.1 and just 110 in tension. Okay, this one is what we obtain. So a certain amount of plastic deformation in compression. I've chosen 0.5. So half plasticity, half damage. In tension instead is 0. So as you can see, every cycle in tension unloads with the second stiffness and goes back to the previous value in compression. Then, of course, you can do other tests. For example, in this case, I'm doing a uniaxial test. Let's say you want to see how this model behaves in shear, in pure shear. Then you can just change the tested component to gamma 1,2, which is the in-plane shear. And then let's say it should be a pure shear, so I need to fix this one in tension. And then I go and see the output here of this one. Okay, so this is the behavior shear in one direction. If I want to increase the, oh, now I can put it 1 and 1 because actually I want to push it in the same way. Let's see what happens, for example, if you put some pre-compression in the vertical direction. Let's put, I don't know, -1. Okay, it increases the strength and so on. Okay, so let's say this is fine. This is concrete in 3 dimensions. Now you need to take care about one thing. Before we were working with uniaxial models, and with uniaxial models, we just created the model and that was fine. Now we're working with 3-dimensional models, but OpenSees called them ND. ND stands for n-dimensional. We have many kinds of n-dimensional models. It can be a 3D, it can be a 2-dimensional model, so plane strain or plane stress, or it can be a thick shell model. A thick shell model is like the 3D, but without the out-of-plane stress. So it has just 5 stress components. And fortunately, in OpenSees, you don't need to develop a material model for every kind of dimension. You can just code, as I did, the 3-dimensional model, and then in OpenSees, you have the so-called wrappers. For example, I want to use this one into a shell model, like in this example, so I can convert it into a plate fiber model. So let's call this one concrete plate. I go under model material ND, other ND material, and here you have a series of wrappers. This one is called plane strain. It takes any 3D material and converts it to a 2D plane strain material. Same thing for the plane stress. Plane stress layer is the same, but creates a layer. And then we have the plate fiber. Plate fiber is the one that converts a three-dimensional material into a plate fiber material. That is a material where only the constraint of having the sigma z equal to 0 is applied, okay? It's pretty much like the plane stress, but without the constraint of having the out-of-plane shear equal to 0. So in this case, if you use the plate fiber, you can also consider nonlinear out-of-plane shear. So the only stress which is neglected is the out-of-plane stress, which makes sense in shell because we don't have out-of-plane stress. And it is very easy. You just need to say what is the three-dimensional material that I want to convert. And of course, it is the concrete 3D. So at this point, this material model is the 3D. This one is the one for the shell. Now, the next step is to define the rebars. Now, once again, for the rebars, you have two choices. You can either use a J2 plasticity in 3D, but it is not convenient because OpenSees has many material models for reinforcing rebars in uniaxial models. And then there is another wrapper that converts these uniaxial models into equivalent smeared plane stress layers. So we can just create a uniaxial steel as we did for the beam case. We can call it beam uniaxial. And we choose one of them. We can choose the same one we have used in the beam case. So we go under steel reinforcing steel, and we choose steel 02, which is the Menegotto Pinto model. And in this example, I've used, let me see, the parameters for the steel. Okay, for some reason I didn't print it, but anyway, I choose a value, then you can see from the real one. Oh no, I have it here. Yes, it is 476. Then these parameters that define, if you remember, the hysteretic loop, I've chosen 30, 0.925, 0.15, and then I calibrated this B parameter, which is the strain hardening, to a value of 0.015, because in this experimental test, here, there are some pages about the material models, slightly above. They show a quite good hardening in the experimental test for steel. Here it is. So I calibrated the B model to reach this kind of ultimate strength for this strain here. And it turned out to be 0.015. And then the stiffening Young modulus is 1,9,000. Is it fine? I don't see from here. Okay. Once again, let's do a test just to make sure everything is fine. Okay, this is the kind of behavior that we obtain. Perfect. Now this is steel, but it is fine for uniaxial. Now we need to convert it to a plate fiber. Now to convert it to a plate fiber, you can just create, oh, and if you go and look at this example, here you have all the drawings to understand how the rebars are placed. Let me show you. Okay, here. Well, basically here in the web, we have 6 diameter rebars every 180 millimeters of spacing. And then we have different diameters in the beam columns. And for simplicity, we are going to neglect the rebars in the bottom and top beam because it is not so important. They're so massive that these rebars are not doing anything in our example. If you want to be more precise, you can change the file that I will send you. So we are going to create 2 layers, one in the 0 direction and one in the 90-degree direction for the web. So let's go here, how you convert a uniaxial material into a plate. So let's call this one rebar layer at 0 degree. We go under material, ND, other ND materials, and it is a wrapper, pretty much like the plane strain, but it is called plane stress rebar material, or no, not plane stress, but plate rebar. It is not here. I think it is. Yeah, it's one. Materials for modeling concrete walls, plate rebar. You choose a material, which should be a uniaxial material previously defined. So we go here and we choose steel material, and you choose an angle. So 0 for longitudinal and 19 for transversal, but actually here, first of all, they are the same, so it is not important, but they are aligned with the shell axis. Okay, so 0 means aligned with the x-axis here, so longitudinal in this case, and the other 90 with the y-axis. So we can clone this one because it will be the same, and just change the name and the angle. So 90 degree, oops, 90 degrees, and I put 90 here. Okay, now we have these two layers, and basically we are now ready to assign, to create the nonlinear layer cross section for the shell. So how do you do this? You go here, add, and you can call it web RC section. You go in section, and you have the layer shell. Layer shell basically allows you to define a custom number of material and a custom number of material thicknesses. For every material, it will generate one integration point that has the weight of that thickness. Now, in this case, in our example, the total thickness of the wall is 100. So we are going to create, let me remember what values I used. But it is not important to have so many integration points in this example because there is no out of plane bending. So I will just use 6 integration points through the thickness, and I will use 4 of them for the concrete. So I will put 25 and 25 millimeters here, 25 and 25 here. So the total amount of this one will be 100 for the concrete. And then in the middle, I have to put one layer along the 0 degree of, along the 0 angle, and one layer for the 90 angle. Now the problem is, what is the thickness of this layer? You have to find an equivalent thickness. Now in this case, we have, in this example, we have a 6 diameter rebars placed at 180 spacing. So here the equivalent thickness would be the area of one rebar divided by the spacing, which in this case it turns out to be 0.175. So the area of one rebar divided by the spacing. And same thing for the vertical, because they are same diameter, same spacing. Okay. So basically this one will give you the equivalent thickness that multiplied by the area of the element will give you the same amount of rebars, basically. So it's a way to define the rebars in a smeared fashion. So 6 layers of thicknesses, and of course we need to create 6 layers of material models. And they should have the same order in order to go with the appropriate thickness. So we create 6 layers. The first 2 are concrete plate, same here, concrete plate and concrete plate, and in the middle we put rebar 0 and rebar 90. Okay, so this is our layout of our composite shell. Our section, now here I'm just writing it down just to remember, so it is 6 every 180 millimeters. Okay, so this one is the cross section for our web. We can directly assign it, so we are in the property. Now, when I was assigning material models and elements to the previous example, I just used the full selection because every geometry had just one material model. Now, in this case, I have just one geometry and I want to assign different material models to the different components. So how do you do if I go here and I can just select the entire geometry? Well, there are 2 options. You can either go into the worktree, expand the faces of the geometry and select them one by one, but this is not convenient. Otherwise, you have to have a look at these buttons here. These buttons here allows you to change the selection mode. For example, if you move the button, if you move the mouse over the button, it will give you some information. This button here is saying if it is checked, you will select the entire geometry. Otherwise, you will select sub-geometries only. Okay, and you can select some geometries of the types that are checked here. So I want to select vertices, edges, faces, and solids. Now in this example, I just want to select faces. So I switch off everything just to make sure I don't accidentally select one edge. And so I can select only faces. Now in this example, I want to assign this one only to this face. So I can select it and drag and drop. Okay, and now you will see it changes the color according to the color that you have here. Of course, I didn't say it, but the color is defined by default. If you want, you can change the shader, whatever you want. So you can change the appearance of your model just by changing the diffuse color, transparency, and so on. But this is not so important. Okay, so we have the material model for the internal shell. Now we want to create the same model for the bottom beam and the top beam. As I told you, basically it is the same concrete. Well, actually, in the experimental test, it was slightly different, but a very small percentage. So for simplicity here, I will use the same. The only difference is the thickness. Here, the thickness of this wall is 100. The thickness of these two beams is 400. So we need to create another, and also the reinforcement is different. As I told you, I will not use any reinforcement in those two beams, but if you want, you can change it. So the concrete is fine, concrete plate is fine. We just need to define another layer. And I will call this beam RC section. Not to confuse them with the lateral beam because we are going to model them as real beams. Here I will write top, bottom, beam RC sections. There are beams modeled as shells. So we go under section once again, layer shell. Here we choose the same amount, the same number of layers. I thought in my previous example I've chosen 5 layers only. All the layers have the same material, concrete plate. And then I also choose 5 layers of thicknesses for a total amount of 400. So 80 each one. Okay. And this is my material model for these 3 faces here and these 2 faces here. And drag and drop. Perfect. Now there is this fake geometry here, which is only used to create a sort of kinematic constraint to make it rigid. Why I didn't use a kinematic constraint and instead I'm using a rigid material? Well, for just one reason actually. It's for the ease of users. If I created a rigid body constraint over here with this point, then the reaction at this point will be transferred to the slate points. And it is a mess then to go and check the reactions here. Then you have to sum the reaction, export it to a graph. Instead, if I keep it like this, I can apply a displacement here at the top and read the reaction directly here. So it's easier for me in this way. So I can simply choose a stiffer material for this one. It will be elastic, so I don't need to create nonlinear material models and then put them into a fiber section. I just create an elastic plate section with a stiffer material. So elastic, stiff section. And if you want to model an elastic section for a shell, there is this one called elastic membrane plate section, where you just specify the Young modulus. And here I've chosen, I think, a couple of orders more than concrete. Well, not that much, just a double of concrete, so 50,000. Then Poisson ratio, and the thickness, which is the real one, 400. So it doesn't need to be much stiffer, just the double of the concrete and it's fine. Okay, and this is ready to go. Since it is elastic, of course, I just can use an elastic section. Perfect. Now, I think we have all the material models. Let me check. We need something else for the beams, but for the shell is fine. So we can go now here and check the element properties. Now, before assigning the element properties, I want to explain you something. The meshing, okay? Now, if you go and look at this geometry here, we have a series of quad elements. They can be safely meshed as quadrilateral meshes using a structured mesh. Instead, this one is not candidate for structured mesh because it has not been divided. If you want, you can divide it and you can create quadrilateral zones in such a way that it can be meshed using a structured mesh. But since we don't need to read any stresses here, it is not important, it's stiff. So we can use a triangular mesh here. Fortunately, we have both a quadrilateral and triangular shell element in OpenSees. So for example, if I go in mesh, and just to make sure that everything is meshed correctly, I can set a global seed to a size of, I don't remember, I think it was 150 or 200, sorry. Yes. Then I go in mesh control, which is something that I didn't show you before because mesh control does not make much sense with edges, but with faces and solid, it makes sense. So by default, everything is as an algorithm, which is unstructured, and as a topology, which is triangle and tetrahedron, which is the most general one. If you want, you can change it. For example, I want to select some faces here, these three and all of them. And for these faces, I want to use a structured mesh with a quad hexa meshing, linear displacement interpolation. We don't need quadratic elements. So assign and done. Now, when you mesh it, you will see a structured mesh down here, and then some triangular mesh up here, which is not important. As I told you, this is rigid. Okay. Why I've shown the mesh before? Because you have to choose the element according to the mesh. So if here I use quadrilateral elements, quadrilateral mesh, and here a triangular mesh, I have to choose a finite element accordingly. This is one limitation of OpenSees because it doesn't have, for every material formulation or any element formulation, it doesn't have all the possible geometries. So you have to know them. Okay, so we go back to property. We need to define two elements for shells. One which is quadrilateral, so let's call it quad shell. And we can choose, we go under shell, we have many of them. Now I will give you a brief introduction to these shell elements, and I will talk about them Wednesday when we will be doing a webinar on the out-of-plane behavior. Now, as I told you, this problem is actually plane stress, so it doesn't change that much what kind of shell I choose. Now, the first one, don't ever use it. It's simply an elastic shell. I will never use it. Then you have the MITC4, which is the typical shell that you can find in Abacus. It's one of the most standard shell you find in every finite element solver, and its quadratic counterpart. This one can have either a linear or a non-linear kinematics. Then we have, and this one has the out-of-plane behavior is the thick plate theory, so Reisner-Middling theory, and it accounts for out-of-plane shear. Instead, the DKGQ and DKGT assumes the Kirchhoff behavior, so thin out-of-plane behavior. They have the same formulation though, so they have a very good formulation for the in-plane membrane part without special formulation for the drilling degrees of freedom. Then we have the NL and here counterparts of these two, which are nonlinear kinematics of these two here. And then we have the thermal just for people doing thermal analysis, but it is not important for us. So in this example, we are going to choose the DKGQ. And tomorrow I will show you instead that these ones are not so good for the out-of-plane of micromodeling. I will show you Wednesday what it means. But for the moment, they are fine. And they have no parameters, so you just need to choose the finite element and you're fine. And we do the same for the triangular. So shell. We choose the same formulation, so shell DKGT this time, where T stands for triangle. Okay, so now we can select all this geometry here, and we can drag and drop the quad shell, and this face up here, and we can drag and drop the triangular shell. Okay, we are fine. Now let me save it before going ahead. Okay. So now we have physical properties and element properties for all the shells. Now, if you have a look at the experimental test, we also have beams, lateral beams here. Since they have a more dense, a denser reinforcement, probably it's better to model them as a beam. That is not that important, but in this way I can show you how you can mix different kind of models. Before we have seen only beams, now shells, and I will show you how to mix shell and beams. Now, the nice thing about beams and shell is that they share the same degrees of freedom. So I can just create properties for a beam and assign it to the edge of a shell, and it will automatically create an element attached to the shell. Okay. Now, keep in mind that this is fine when we are working in 3D with shell and beams because they share the same degrees of freedom. But if for some reason we model a wall with solids, we cannot attach a beam to a solid because then the degrees of freedom are different. The solid is only displacement degrees of freedom, the beams has also rotation. So you need to do another trick, but I don't think it is necessary to talk about this now. In any case, you need to draw the beams as a detached geometry, and then you use a kinematic constraint to attach only the displacement degree of freedom. Now, in this case, we are lucky because they share the same degrees of freedom, so we can just assign material properties to them. Now, since we are going to model the beams as a nonlinear distributed plasticity model, we need a fiber cross-section. So let me see the dimension of this fiber. And of course, since we need to do a fiber cross-section, we need a uniaxial material model, which has pretty much the same material parameters of this one. It was slightly different in the paper, but let's keep it the same. Create 1D. And also here, you can choose any of the uniaxial material under concrete, or you can go under plugin and you choose as the software damage TC 1D, which is basically the same for the 3D, but in 1 dimension. So probably it's fine, it's better for you because you can reuse the same parameters. Here they are the same, but you don't have the parameters defining the surface, the latency, and this stuff because it doesn't make sense with a 1D model. So you just need the Young modulus. Let me go and see. 23,000. Yes. Of course, you don't need a Poisson ratio here. So the tensile strength 3.2, 0.075. Then here we have 20, 30, 10, 0.003 big strain. Probably I put too much zeros. 0.003, okay. 100 here. These values are the default ones. And then we had 0 and 0.5 plasticity in compression and the implex integration scheme. Okay, perfect. So we have the concrete 1D. The steel is already there because we used uniaxial steel also for the shell, so we can reuse the same steel for the fiber cross-section of the beam. And so we can directly now create the fiber cross-section for the beam. So we go in add, beam fiber section. And you have seen this already before, so it will be slightly faster here. Rectangular fiber section. So we need to specify torsional constant as we did before, and it was in this example. Let me see. Well, actually, this assembly is not so important. We can put 1 to the power of 10. Then we have 3D. The size, it was 150 and 200. It's quite small. The cover is 10. Then we have rebars of 12 diameters. Let me change all the diameters first. Then I change the number. And then we have only 1 per corner and 1 per side. this, and the material model. So this one is the material for the rebar, and then we use the same material model for cover and core. We don't want to compute the confinement. It is not important in this example. So the stirrups values are just random. You don't need them. And we are fine with the fiber cross section. Perfect. Now, as we did before, the fiber cross section is not enough. We need to create the beam property. And in this case, we're going to call this one beam property, as we did before for the distributed plasticity. So we go under special purpose, beam column, beam section property, standard integration point, Lobato is fine. Now, since the beam is attached to the shell and is already discretized in many pieces, we don't need so many integration points because we already have a lot of pieces. So I use just the minimum, which is 2 integration points per element. And all of them have the same beam fiber section. Okay, so this one is the one that we can assign to these edges. Now, as I did before, you remember I am in a sub-selection mode because I switched off this one. But in this way, I can select only faces. So I can just switch off this one and switch on this one for selection of edges. And now I can select this, and this edge here. Why I'm selecting also these ones? Because in this way, the reinforcement passes through the top and bottom beam. I have an overlapping of concrete volume, but it's not that important. Okay. And now I can simply drag and drop the beam property. Then I do the same for the beam. So I create a beam element. Okay. As we did before, we go under model, beam column elements. Now, in the previous example, since I was using only one finite element for the entire member, I've used the force beam column. But as I told you in this example, since the beam is attached to the shell, and the shell will be discretized in many pieces, there is no need for using a force beam column. It is sufficient to use a standard displacement beam column. It will converge faster, and there is no need for the computation for the extra computation required for the force beam column. So you can just go with displacement beam column and choose 3D. Now you have to select the same edges to assign this one. And sometimes it's easier, for example, to reuse the selection of a material. For example, in this case, I want to assign this element formulation to all the entities where I had assigned these beam properties. So again, simply go here, select. So I have the selection associated with this material, and then I drag and drop the element property. So now these and these are assigned to the same entities. Okay. So we have also the material, the element properties, and they are all. Now we can go with, just one thing, yeah, you have to notice. If we go and see the drawings here, I think the beams were rotated in the other direction. Here it is, let me see. Yes, 150 is on the frontal face. And I think here we have it in the opposite direction. Yeah, so as we did in the previous example, whenever you want to change the orientation of something, you need to use the local axis. So let me see the default local axis here. On these edges, I have the Y pointing in this direction, along the global Y direction, okay? So what I need to do is to simply create another local axis that points the Y in the Z direction. So for simplicity, I switch on the grid, okay? I put on the front view, and then I go on local axis, add. Why I was using the front view? Because now I want to put the let me see how is the local axis. It is pointing. Well, actually, it is not necessary. I can go just on the top plane. Yes. Because now I want to put the y-axis not pointing as the default. The y-axis by default is pointing in the global direction. I want to point it along the x direction. Okay, so that now I can select my material, my entities where I assign the beam. So select, and I can simply drag and drop this one, and you will see how them will rotate. So I drag and drop this new local axis. Okay, now they are oriented in the opposite direction. Okay, so we can save this one because we are done with the geometry, constitutive modeling, and element properties. Now we can go to boundary conditions. Okay, so for boundary conditions here, we have, as usual, a fix at the base. So I want to switch off, yes, because the grid. I'm going to the front view, and I first create the fixity for the bottom. So I can call this one fix bottom. Then I go in model, constraint, single point, and I choose fix. In this case, we are in 3D, and we want to fix everything, both displacement and rotation. So I just check every component, and I do my selection. So all the bottom part of this beam. Press OK. So if you want to see if everything has been assigned, I go in under condition, and I will see the labels for, for the condition. Now, the other condition is the self-weight. Oh, so this is another nice feature that we have in OpenSees, in STKO. Those of you that know OpenSees, you may know that assigning the self-weight or distributed loads sometimes can be very annoying in OpenSees, because some elements has the option to assign the body force directly in the element formulation, but not all of them. For example, the shell elements does not have this option. And even if you have this option, that load will be applied instantaneously. It cannot be applied as using a load multiplier. So if you're using OpenSees manually, the only option that you have is to do nodal lumping manually and to assign equivalent nodal forces all over the mesh. Now you understand that this is not so easy. You need to create your own scripts. They will work with some elements, but not with the others. So it's very annoying. In STKO instead, it looks like there is this kind of distributed load, but it is not true basically. The user thinks that it is assigning a surface load or a load distributed on an edge or on a volume. And in STKO, we directly do the nodal lumping while we are writing the Tcl file. So basically, you assign a load on a surface, and when you write the Tcl file, we write the equivalent nodal forces for OpenSees. So this is something very, very useful. So I will show you. Now in this case, we want to create the self-weight for the web. And you may ask, why are you creating the self-weight for the web and not for everything, because they have the same self-weight? I'm going to show you now why. So web self-weight. A web self-weight, since it is a surface, we need to create a load, which is a force, and which is a phase force. Now the phase force, of course, is a force over an area. So we cannot directly use the self-weight. We need to use the self-weight multiplied by the thickness. Now, since it has a the web wall has a thickness, and the two bottom and top beam has a different thickness, we assign two different loads. So for the web, so for the concrete here, we assume 25 kilonewtons per meter cube. And so here it should be multiplied by 100 millimeters. So it was minus 0.0025 Newton millimeter square for the web, and I assign this one and I assign it to this. Okay, so I have my distributed load acting on tangentially on the face of this shell, and I do the same for the bottom and top beam. Self-weight, constraint, not constraint, sorry, load, force, phase force. Now this one should be the same, but multiplied by 4. So it was minus 0.01, because the thickness of these two beams are 400. So I select these faces and I assign it. So now we have the load all over the place. We could put a load also for the beam, but it's not so important. Actually, even the self-weight is not so important, but I just wanted to show you. Oh, another feature that you can have with the self-weight, now I'm just going to show you, but it is not necessary in this example. But we have another feature if you have to assign complicated self-weights, like here we use a mode which is constant. Constant means constant vector for the entire locations. Otherwise, you can use a function. Okay, if you use a function, then you can specify a Python expression for every component. Now, let's say, for example, I want to put a minus something, let's say minus 1000 times the distance from 0. I don't remember 0, I think it was here, so times x. Okay. Now you can see the load that now linearly increase from here, here actually it was 0. So here they become positive because it was a negative value times a negative distance, and here they become negative, okay? And you can use whatever fancy thing you want. If you know Python and you know the Python expression, you can create, for example, expression to assign, I don't know, the wind load over an entire wall, if it is a high-rise building, whatever you want. Now, this is what just to give you a brief introduction of what you can do with this kind of automations. But of course, in this case, we don't need it. Just a constant value is fine. Okay, let me save this one. So now we have boundary conditions. We need the last boundary condition, which is an applied displacement on top of this rigid beam here. So we go under condition, new. I call this one push, as we did before. It is a load. Since it is an imposed displacement, we go under SP, which stands for single point. And it is 3D UR, displacement rotation. And we just want to push in the X direction of a total amount of 28.6 millimeters. Okay. Of course, I need to do my selection first, then press OK. So we have also this boundary condition properly defined. Now the boundary conditions are fine. We just need to go to the analysis steps. So let me say 5 once again. As I did before, the analysis steps define the way you go into the analysis. So as a rule, I always use the recorder as a first step. This is not necessary, but you can place it later on. But the recorder will start recording only the things that are defined after him. Okay. So if I put the recorder at the beginning, it will record everything. If I put the recorder after the gravity analysis, but before in this case, the pushover analysis, it will record only the pushover analysis, okay? So don't put the recorder at the end because it is useless otherwise. So we go on the recorders and PCO recorder. We choose a name. Here we can choose results. And I want to see displacement. I don't need rotation actually. Reaction force, yes, because I want to extract the load displacement curve. Now in this example, since it is cyclic and we have many cycles, I will only plot, since we're going to do something like 10,000 time steps, I only want to record only 10 time steps just to keep the database smaller. And then what we want to see, we want to visualize, for example, section forces, section deformation. This section forces, section deformation will give us both the beam forces and deformations, and also the shell forces and deformations. So the stresses integrated over the thickness for the shell, or the stresses integrating over the area for the beam. So basically this one is a result on a Gauss point. But then we also want to plot stresses and strain in every fiber. Same thing for the beams, they will be uniaxial stresses, so just scalars. For shells, they will be a three-dimensional tensor, actually with only 5 components, not 6, because this kind of shell doesn't have the out-of-plane stress. Okay, now there is another, before I didn't use it, but now we have an option. This kind of material model that I put in OpenSees, it has an extra result, which is not common to every material, so that's why you cannot find it here. But in this model, you can ask for the damage variables, so positive and negative damage, and for the equivalent plastic strains, positive direction, negative direction. But how do you do if they are not the common ones that are here. You can use the same concept, but using the custom element results. So with the custom element results, you can ask every result that you know are available in some element or some material, but are not among the standard ones. The only rule that you have to remember is that, and you can find this one in the documentation for the MPCO recorder. If you specify only a name of a result, like here, force, it means that you are asking for a result at the element nodes. So in this case, force is basically the element internal forces brought to the node, which is basically for a beam, for example, the inverse of the reaction forces. Instead, if you have section dot the name of the result or material dot the name of the result, means I want to record this result on the Gauss point. Now for beams and shells, OpenSees uses the section keyword, while for solid elements or trusses, it uses the material keyword. But it is the same. Here, section dot or material dot means for every Gauss point. If instead you want to record something on each fiber, you need to do the same thing. So section dot fiber dot and the name of the result. This means for every Gauss, for every fiber in that Gauss point, I want this result. So you need to understand this kind of namespace, because you have to use the same here. Now, if I want to record a damage variable, I know that the result of my material model is called damage, for example. But my material model is inside a shell with a fiber cross-section. So what I need is to say section, that means for every Gauss point, fiber, for every fiber, I want to record the damage result. This damage then will be a vector of two components, positive and negative damage. And the same here, but I just changed the name of the result, which is equivalent plastic strain. Okay. So this is a way to ask custom results. Now you may ask, how do you know a material model or an element, what kind of result it has? Well, you can go on the OpenSees. Now let's say, for example, let's say this one implements this thing. No, this one doesn't say anything, but in some material model, you see a note and it says, this material supports the following results, okay? The problem is that you need to know OpenSees quite well to understand it. So that's why we have the default ones here. And only in those few cases where you need extra information, you need to be aware of what kind of results are supported by that material, that element. Okay, so we press OK. And we save it. Now for the second stage, as we have done before, we add the constraints. So the second step is to apply the fixed at the bottom. So we call it add boundary conditions. We go under pattern, add pattern, constraint pattern. And in this case, we just have one single point constraint at the bottom. So we just select the fixed bottom and we are fine. We don't have any multi-point constraint here because the only stiff constraint that we needed actually has been modeled as a material here, as a stiff material, not as a kinematic constraint. Okay, so second step is to create to add the vertical load. So add the load. You go under pattern, add pattern, load pattern, and here you find soon a mistake. I need a time series, but I didn't create anything. So let's get rid of this. We go under definition, and we actually need to create two different time series. A linear one, which is used for the vertical load. So we just can go to time series linear. That goes from 0 to 1, and this is fine. But then we are going to simulate these this cyclic test, and here somewhere you can find all the load protocol that I already extracted for you, and you can find it in the day one RC wall. There is something called load protocol here. Now the first column are the time, and the second column the load multiplier for the displacement. Actually, they are normalized. The time, of course, is normalized to 1, and the displacement are normalized to 1 as well, because in OpenSees we are assigning the reference value here. Let me show you under the condition. Here in push, we have assigned the real value, the real ultimate value of the displacement. That's why the time series we use it as a normalized one. Otherwise, we can do the opposite. We can use 1 here and put the real displacement on the time series. It's the same. So for creating a custom time series, like in this case, because we want to simulate a custom load protocol, I call it Cyclic. And then in OpenSees, you have the path time series. The path time series is exactly used for this scope. So here you have 2 options. It can be constant or non-constant. Constant means how the time interval is specified. If you choose constant, you can just put here a vector of values and a custom time increment. But in my case, the time increment was not the same, so I choose non-constant. And then I have to specify both a list of times and a list of values. So I go here in list of times, I go back into this file and I select these columns, and I simply copy, paste them here, okay? Okay, and then I do the same here for the list of values, which are instead the load multipliers, which are these ones. Okay, so once you load both of them, you can see the output here, how it looks like. So you have some small cycles, and then they keep on growing up to the last displacement. Then I want to show you a little note, because the path time series is very flexible, but then in OpenSees they use an assumption. If the analysis goes even a little bit after the time step of 1, and you didn't define any value here, it will drop to 0. Okay. Now in this case, the ultimate value is exactly 1, but the problem is that when in OpenSees you are doing the time increment, you can have a very small round of error, so it can be 1.0001, and for the time series it's like being outside. So when I specify a path time series like this, I make sure that my analysis would finish at 1, but just to be safe, I add another value at the end, so I make room for 1 more, and at the end I put the same value that I have here, so -1, and I do the same here. I make room for another entity. So here the time was 1, and then I put just 1.1, just to make sure that if OpenSees makes a small mistake, I am safe, okay? It doesn't drop to 0, basically. Okay, so this is the linear, the cyclic. So let's go here, vertical analysis, or vertical load. And I go under pattern, add pattern, load pattern. And for this, we choose a linear, because the vertical load will be applied linearly. The load is a distributed force, and so it goes under load. We have, well, actually we have 2 of them, one for the web and one for the bottom and top beam. Okay, so 2 loads. Okay, then we are ready to create the vertical analysis. So we go under add vertical analysis. We go under model, analysis command. So it is a static analysis. Let me see all the settings that I chose before. Static analysis, penalty method. As I told you, I cannot use the plane constraint because I have an imposed displacement. Now here a good value is 1 to the power of 15. I already told you how to compute a good value for the penalty. It's not written anywhere basically, but there is some notes by Professor Filippa that explains what should be the best value for the penalty parameter. So as I told you, try to estimate the typical stiffness value of that. Actually, what you need is the stiffness at 1 node of your matrix here. Now, actually, you don't know this, so try to estimate it. It can be 1 order or 2 more than the typical Young modulus. So, for example, here the order of the Young modulus is 5. It's 3 to the power 5. add a couple of numbers there, so it will be 6 because more elements converge to the same node, and then you have the thickness of the wall, which is 100. So it will be 7, and then you add 8 to that number. Why 8? Because 8 is half the number of significant digits for a double. So a double can represent up to 16 significant digits. Then you add 8. In this way, you obtain the maximum number that gives me the best accuracy. Okay. So it is a compromise between enforcing the constraint and keeping a good ratio between the eigenvalues of the stiffness matrix. So remember the order of magnitude of the largest entry on the stiffness matrix plus 8. Okay, so we're fine now. In the example that I've done before, I've only used OpenSees sequential. Okay. Now in this example, you will see it when you will download it. I'm not using OpenSees sequential. I'm using the parallel version of OpenSees, but not because I want to do parallel analysis. Since this model requires more computation than the other, I will show you that you can use the parallel version of OpenSees, not because you're going to do a parallel analysis, because we will talk about parallel analysis Wednesday, but because the parallel OpenSees has a new solver, which is called MAMPS, that is much faster than this one. So even if you use just one single processor, it will be much faster. If instead you have problems running the parallel OpenSees because for some reason in your computer it doesn't work, because it is optimized for some CPU architectures, you can safely go back to this value, okay? Now, in the example that you will download, you have a parallel number, which is the only one, and the MAMPS. MAMPS solver is the fastest one that you have here. Then I have a Newton method for the algorithm. Normal balance test is fine. I put it 1 to the minus 6 and 100 iteration at most. And yes, I want to print the convergency so that I know if it is converging or not. Then I want to do a load control, and 10 steps are enough because the vertical load is not so high. And as I did before, when we finish this vertical analysis, we want to keep the previously defined load, so the vertical load, constant, disregarding the new time step. So we can reset the pseudo time step to 0. Okay, that's why we can use the cyclic that starts from 0. Okay, so you can accept this, and now you have the vertical analysis set up. Second step is to add the horizontal load. Push. Then you go under pattern, add pattern, load pattern, and you choose SP because the horizontal load is an imposed displacement, and you go under push. Okay. Now you can choose a time series. Here you have two options. The file that you will download has the cyclic. Okay. But actually, if you want to do some test in a monotonic fashion just before doing the cyclic test, because I typically first compute the monotonic envelope to make sure it is properly representing what I want, and then I do the cyclic. You can safely change from linear to cyclic. Why? Because both of them start at 0 and both of them finish at 1. That's why I use the load constant here. So I can safely change between one and the other. Okay. So now in this example, I have cyclic, but you can safely change to the other one. Okay, and then we need the last analysis. It is very similar to this one, so I clone it, and I can edit it. Not actually vertical load. I made a mistake. I need to clone the vertical analysis. Right click, clone, clone. And then I can edit it. Horizontal analysis. It is still static, penalty method, parallel number, MAMPS, Newton, normal displacement is the same. It is a load control, but here I will show you something. Before, Fabio asked me how to use in STKO a custom command that is not available in STKO. Now, in this case, I will show you the same thing. So first of all, I get rid of load const because I don't need it. And I put a lambda of 0 and 0 increment here. So basically here, I'm not analyzing anything. I'm just defining the analysis. Why? Because I say I'm not fine with this kind of fixed number of iterations, this fixed number of steps. Because what happens if, for some reason, my model does not converge? I need to use a smaller time step, but in an adaptive way. And also, I don't like the way OpenSees print these results because it just gives me a huge amount of lines and I don't understand where I am in my analysis. So especially when my analysis takes a lot of time, I would like to see a percentage of the analysis to understand if I'm almost done or not. So here what I do, I simply define the analysis, everything I need. Then I say don't print anything and don't do any automatic analysis. I will do something later. So this is just a definition. Then I add a custom command, which is an adaptive time step. Actually, in few weeks, this one will be incorporated directly in STKO. But for the sake of this example, I want to show you how to add custom Tickle scripts. Let's call this one adaptive stepping. So we go under miscellaneous command, custom command, Tickle file. Now, don't worry, you don't have to be able to code a lot of Tickle because in the folder here, I already have an example. It's called adaptive time step. So you can open it. You can just copy paste everything. Control C and Control V here. This one basically is a script that now I will just give you a brief introduction of what it does. So the total time of the analysis. Now my analysis, the horizontal analysis will last 1 second because our cyclic protocol lasts 1 second. Then you can specify the initial number of increment that you would like to have. Now in this example, I think I've chosen 10,000 because it has a lot of cycles, but you can use less if you want to do a first check. Then you have some parameters that define how the time step should be adapted. For example, it cannot be larger than the initial time step, which is 1 divided by 10,000. So the max factor is 1. The minimum factor is 1 to the minus 8. It means if it doesn't converge, I can reduce it up to 1 to the minus 8, the initial increment. Then you have a few parameters that define how fast this thing can be incremented. And then you need 2 other options. You can leave it as they are, but if you want to edit them, we need a maximum number of iterations, which should be equal to the number of iterations that you specified here in the analysis, which was 100. And the desired number. Desired number is the number that you would like to have. This is the maximum, this is the desired one. Typically, this one should be, of course, less than this one, otherwise you will not obtain any adaptation. And I usually take it as half this one, okay? Then I do a few other stuff. For example, I want to measure the total duration of the analysis here, and I want to print the total duration down there. And then instead of doing what OpenSees does, which is analyze n times the same time step, I do a cycle. And I do, okay, for each cycle, do a single analysis for a time increment. If it is fine, well, I print something. And if I used few iterations, I increase the time step. You can see it here. If it is not fine, I decrease the time step. So I say an error, okay, current factor, okay, reducing time step due to non-convergence, blah, blah, blah. I say a couple of operations here. But the idea is that this algorithm will try to find a time increment which is the best one for ensuring that you reach the 50 number of iterations, so the desired number of iterations, okay? So this is not so much important in this example because our material model with the implex method is always convergent, so you don't need that one. But it's useful for you if you are doing very nonlinear analysis with some other material model. And then something else that I wanted to do here is to print something in a nice fashion. For example, here I'm printing the number of increment, the number of iterations that I've done in this increment, the last norm that I've reached in this increment, and the percentage of the analysis, which is something that when I do lengthy operation on OpenSees, I'm never aware of. So I don't know if it is about to finish or not, or how much I have to wait. Okay. So let's press OK, OK. Perfect, I think we are done. Now the mesh is fine. Since I'm using the parallel solver, but I told you just one processor, I need to do a partition with just one processor. So I create partition with just one partition and done. Now don't focus too much about this because Wednesday I will talk about parallelism, how to use more partition and more processors. Now, as I told you, I'm just going to use it for using OpenSees MP. So I can go to OpenSees MP in such a way that I can use the MAM solver because the MAM solver is not available in OpenSees standard. And now you can run the analysis, okay? Now, of course, I already have all the output for this. Just to show you, so this one is the vertical analysis. And then here it is starting doing the horizontal analysis. And probably I changed something, but it's fine. You will find the correct values on the other side. So here I have the values already run, and it is this one. This will take something like 15 minutes to run. So that's why I have already the output. And it is RC wall. Okay. So by default, when you load it, it loads the deform shape, but you can use something different like the beam shell fiber color map, for example. And as you can see here, you see all the fibers for both the shell and the beam here. Of course, the results are different because you have section fiber stress over surfaces or over lines for the beams, okay? So for example, if you want to see the damage over the beams or over the shell, they are already in all the size. Okay, here it is at the very end of the analysis, but at the beginning you will see, okay, something like this. The initial crack pattern is kind of smeared over here, like in the example. The columns are completely broken. And then if you want to see the cracks where they open, you can choose, for example, strain surfaces, sorry. And you can choose the maximum principal strain to give you an information of where the crack is currently open. Okay, so you can run your animation and try to see the crack pattern and so on, okay? And then you can also visualize here, actually it was the point in which this one reached the peak value. Then you can try to visualize what's going on in terms of force versus reaction, as we did before. So the first thing, we need to enable selection of points here so that I can select this point. And I can go under chart data, extract chart data over nodes because I want to extract displacement versus reaction forces. And then here I choose the second stage, which is my cyclic pushover. And I want to plot displacement along the x direction versus reaction force along the x direction. Next, next. Okay, and this is our result. Now I'm not going to overlap to this one, but I just want to show you more or less the output. I didn't spend too much time to make it, to calibrate it a lot, because actually I was doing this a couple of days ago. Let me show you some of the main features. Okay, this one. Okay, this one. So basically you see a reach of a maximum value around 15 millimeters, which is around here. Okay, then a drop, and then you can see, probably I used a too low value for the plastic deformation in compression, but the pinching effect, for example, it can be visible. This one can be visible due to the fact that we use zero plasticity in tension and a certain amount of plasticity in compression, so we can see this kind of pinching effect. So it's pretty fine, but actually you have to, if you want, you can add more features here to add the more information to make it, to play with it a little bit. I actually spent very few time trying to calibrate these models. You have to work with the fracture energy because in this example, there is no information on the fracture energy, and it is quite important. So, but this is now an example on how to use a reinforced concrete, how to create a nonlinear shell with both concrete and reinforcement, and how to do a cyclic pushover analysis. Okay. So if it is fine for you, we can have, if you have some questions, you can ask them now. And then we can do the coffee break, because it is already here in Italy is 16 and 15. So 15 and 50 there. And I think we can have a coffee break, and then the last 1 hour and a half, more or less, will be dedicated to, we will move to Masonry, and we'll start with micro modeling of Masonry. Okay, so let me stop sharing this. We'll start with micro modeling of Masonry, and then we will go to homogeneous modeling of Masonry. And then tomorrow we will do the out of plane, tomorrow, Wednesday, the out of plane and parallelism. So if you have any question about this topic.
No, I don't have question for the moment.
Okay. So if it is fine for you, we can take a coffee break now. Okay, 20 minutes. So we see here at 16:12 Porto time, 15:12 Italian time. Is it okay? Okay.
Yeah, okay.
So see you in 20 minutes.
Professor, I have one question.
Oh yeah.
Is it possible to model material like as you showed us, to assign a material and then apply for the behavior of infill walls, like in plan and out plan, by doing the same procedure as you showed us?
Yes, yes, of course. Keep in mind that it is, I mean, I think what you're trying to ask is if you want to model an infill wall with just
Yes.
one layer, with just one shell,
Yes.
you can use different layers, external layers for the brick and mortar joint composite,
Yes.
and internal layer for the infill. This is fine if you do not expect the two leaves to have some shear deformation in between them. If instead you want to study how this infill can fail, of course you cannot do it, because the shell cross section has the same assumption of the beam cross section, so planar faces. So if it is fine for you, just to have a global behavior of the wall is fine.
Okay, but if I don't have the two leaves, for example, if I have the one leaf wall, then in that case.
Just infill between. Okay,
Yes.
okay. Sorry, I thought we were talking about cavity walls.
No, it's like a one infill in between the frame elements.
Okay, basically you can do the same thing I've done here.
Okay.
With one extra node. So sorry, I understand. I actually was thinking about cavity walls. What I've done here is exactly that, an infill. But now in this case, it's not an infill actually. In this case,
Yes.
it is a concrete wall directly
Yes.
connected in continuity with the frame.
Okay.
Now in your case, if you want to do a concrete frame and an infill wall,
Yes.
you have to take care about how the infill is connected to the frame.
You mean the boundary condition?
So probably instead of doing as I did, where the shell was directly connected to the beam, you can create the beam and the shell separately, and then you can create an STKO, an interaction between the shell and the beams. In this way, in this interaction, you can assign zero length elements to simulate some kind of contact or slip between the two components. Yes. Okay, so it really depends on how you want to model the interaction between them. For example, you can assign only contact material, compression only material, or some kind of cohesion. It's up to you. It's up to what you want to simulate. But yes, you can do it. Of course, they have to be separated. Otherwise, they are in continuity, as I did.